In physics, we will often be asking questions like, where is an object? Which way is it moving, and how fast? To discuss the answers to these questions, we will frequently utilize the concepts of position, velocity, and acceleration. So before we go any further, let's define these terms. Position is simple. It's just where an object is in space. Usually this is discussed with some kind of reference point or axes in mind, and we might express the position of an object as being some distance from this reference point in meters. Velocity is the change in position over time. So if this object travels 5 meters in 5 seconds, it is traveling at a velocity of 1 meter per second. And acceleration is the change in velocity over time. So if this object starts at a standstill and over 5 seconds gradually speeds up to 5 meters per second, then it is accelerating at 1 meter per second, or 1 meter per second squared. So that's how we define position, velocity, and acceleration. Now let's discuss each of these in more depth. When we talk about position, we could discuss distance or we could discuss displacement. The difference here is that distance is a scalar, while displacement is a vector. Let's say you and your friend get dropped off by the school bus at this intersection, and your house is here. Your friend begins to walk down the street and up the driveway, like a normal person. But you find yourself so overcome with excitement to play video games that you decide to plow through the yard in a straight line to the door. Your friend has to walk 20 meters down the street and 7 meters up the driveway for a total of 27 meters. So, using the Pythagorean theorem, we find that you only had to walk about 21.2 meters, and you probably got there a little sooner. What we can say is that you walked different distances, which are represented by these scalar values, but you both had the same displacement because you ended up in the same spot at the front door. This vector, which follows the straight line path, is the displacement vector for both of you, and we can report your position with x and y coordinates like this, 20, 7. Or we could report the magnitude of the displacement vector, which will be equal to the shorter distance you traveled, and calculate the angle off the horizontal using trig functions if we desire, in order to report the direction of the vector. Next, let's look at velocity, which is the rate of change in position. Most people assume that the words speed and velocity are synonyms, and in everyday language they are. But the difference in physics is that speed is a scalar and velocity is a vector. If a group of kids are playing hide and seek and they all run away from the seeker in different directions, it is possible that they all run at the same speed because speed only has magnitude and no direction. So they could all run at a speed of 3 meters per second if they are quick little devils. But each kid would have a unique velocity vector that has a magnitude of 3, but also describes the direction of motion, most likely using the seeker standing still as the point of origin. Velocity vectors will be extremely important as we move forward with kinematics, where we will study the motion of objects. In general, average speed can be calculated by taking the distance traveled by an object and dividing by the time it took to do so. So if you walk 85 meters in 46 seconds, you are walking at an average speed of 1.85 meters per second. To find average velocity, you can do the same, but you would have to divide displacement by time. Lastly, we have acceleration, which is the rate of change in velocity. This is always a vector because acceleration must occur in a particular direction. If you are in a car that is standing still and you press on the gas, the car will begin to move forward with a fixed acceleration. It might accelerate slowly, so the vector may be on the shorter side, but this constant acceleration will cause the velocity to increase at a fixed rate. Let's say an additional meter per second every second. So over 5 seconds, it will reach a velocity of 5 meters per second. Let's say you see a skunk in the middle of the road. It's your most favorite animal, so you slam on the brakes. We can describe this as a deceleration, which is an acceleration in the negative direction. Since you are going from a moderate speed to a standstill in a very short amount of time, this vector will be quite long and pointing back towards the origin. Now we understand distance and displacement, speed and velocity, and acceleration, and we can categorize these as being either scalars or vectors. Before we finish, let's look at a moving object like this marble rolling to a stop, and visualize all three of these vectors as the object moves. First, with displacement, this vector will just elongate as the marble rolls, and will span the distance traveled. For velocity, the vector will point forward as the velocity is positive, since it is moving in the forward direction, and the vector will move along with the marble, but it will decrease in magnitude as the marble slows down, until eventually disappearing when the marble comes to a rest, where it has zero velocity. And then for acceleration, the vector points in the negative direction, since velocity is decreasing or becoming smaller per unit time. But it will be constant in magnitude, since this is a constant deceleration due to friction from the surface it's rolling on. We can view all three of these at once, just to drive things home. Make sure you understand the magnitude and direction of each of these vectors at each moment in time. Let's check comprehension. One of the best ways to do quantitative analysis is to make graphs. When we do this, we are plotting data points that correspond to two variables, and in physics, one of these will often be time. So we can label the x-axis with a t for time, and we could make tick marks for individual seconds, or multiples of 10 seconds, or whatever we want. On the y-axis, we will put some other variable, and right now we want to learn what happens when this variable is position, velocity, or acceleration. Let's go through an example and generate all three of these graphs. Say you are walking on a path in the woods on a fine autumn day. You walk the 1 kilometer path at a rate of 100 meters per minute all the way to the end of the path. Then you sit and rest on a bench for another 10 minutes, thinking about what to have for lunch. Once you've got an idea, you get very excited, so you begin to run back the way you came at a rate of 200 meters per minute. But after you get halfway back, you become tired and you slow down to 50 meters per minute. Let's represent all of this on a graph of displacement versus time. If the point where you started is the origin, and this point on the y-axis is 1,000 meters, where the bench is, we can draw lines to represent each section of your walk. First, you went the whole kilometer at a speed of 100 meters per minute, so over 10 minutes you went 1,000 meters. This line represents that activity because it goes from the origin, the beginning of the walk, to a point with coordinates of 10 minutes and 1,000 meters. Be sure to understand that this line does not represent a path in 2 dimensions. All the motion is along one line, but you are also moving forward in time, and that's what the x-axis represents. Now you are at the bench, and you sit and look at the trees for 10 minutes while thinking about snacks. This means you will move forward in time by 10 minutes, but your position will not change. So this is represented by this horizontal line segment, ending at a point with coordinates of 20 minutes and 1,000 meters. Then, very excited about your pizza, you jog halfway back, or 500 meters, at a rate of 200 meters per minute. So this should take 2.5 minutes. This line segment will have a steeper slope because you are covering more distance in less time. And we can see that we are now at coordinates of 22.5 minutes and 500 meters. Suddenly, you get a cramp, and you have to finish the journey at 50 meters per minute for the last 500 meters, which will take 10 minutes, leaving you at a point with coordinates of 32.5 minutes and 0 meters, back to the place where you started, but later in time. One thing we will want to be able to do is to take this data and draw a graph for the same activity, but with velocity on the y-axis. To do this, we just translate each line segment. For the first bit, we see that we went 1,000 meters in 10 minutes, so that's a velocity of 100 meters per minute. So we can draw a horizontal line segment at 100 meters per minute, extending until the 10-minute mark, because you moved with constant velocity during that time. Then you were at rest for 10 minutes, so your velocity was 0. We can draw another horizontal line segment for that time period right on the axis. Then you began moving in the negative direction, so you had a negative velocity. That sounds strange, but remember that velocity is different from speed in that we are also reporting direction. So here, if we went 500 meters in the negative direction over 2.5 minutes, you had a velocity of negative 200 meters per minute, which is down here below the axis. Then for the last 10 minutes, you had a velocity of negative 50 meters per minute, and there is our graph of velocity versus time. Let's point out a couple things right now. First, we notice that we only have velocity data when the object is moving. When at rest, the velocity is 0, because there is no displacement over that time period. Also, this is quite oversimplified, because it is impossible to go from a standstill to some velocity in an instant. In reality, there must be an acceleration or deceleration when starting or stopping. So that means if we were trying to be as accurate as possible, we would quickly ramp up to this velocity and then ramp down to rest, even if it's over just a second or two. This is important because we will now want to graph acceleration over time. And just the way that we can only have velocity data when the object is moving, we can only get acceleration data when velocity is changing. So there will be a positive acceleration as we just start moving, but it will then come to 0 as we walk with constant velocity. Then acceleration will be negative as we slow to a stop. It will be negative again as we begin to walk back, and then back to 0, but then slightly positive when we slow down our movement in the negative direction. Back to 0, and positive again when we stop, as we require positive acceleration to stop moving in the negative direction. We will only have a non-zero value for acceleration when velocity is changing. In this way, every point on the acceleration graph is telling us about the slope on the velocity graph for the same point in time, and every point on the velocity graph is telling us about the slope on the position graph for the same point in time. If you are well versed in calculus, you know this means that velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time, which explains why we find instantaneous velocity on a position curve by looking at the tangent line. The slope of this line gives us the velocity at that instant, and the slope of the tangent line on a velocity curve will give us the instantaneous acceleration. We will cover all kinds of calculus in the upcoming mathematics course, but for now, we are going to stick to physics without complex math, since we are focusing on basic concepts. All we want to come away with now is the ability to draw and analyze these graphs for position, velocity, or acceleration. So let's check comprehension.